Okay, so as Osni mentioned, so I'm T.Drummond. I'm from the Computational Research Division, and I just want to extend, Osni's words of welcome to all of you. And really, the format of this workshop, we used to have a few more people in the previous years, but we have been just reducing the number so we can maximize the interactions. And I want to introduce two people here. Actually, three people that are here. Matt Nipley, who's going to be talking about PETC. So he's going to be here. So, and I'm going to briefly mention some of the functionality on PETC. Matt is going to extend a lot about PETC tomorrow. Samir, who's going to be a speaker today. And he's going to talk about Tau and, a profiling tool. We're going to have an experience of that this afternoon. But just, so because we have breaks, you can profit and talk to these people. You may want to try to install some of the tools, in your own laptops or your home computers. And this is a good time also to talk and interact with us and Osni, and also the tool developers that are going to be here. So what I'm going to do is I'm going to talk about a little bit about motivation. Osni spent some time already talking about, how the hardware looks. So I'm going to skip to the HPC software stack. And we're going to spend a lot of time sort of going through, what is in the collection, what the tools are, what functionalities, and, and if possible, I'm going to make references to tools that are not in the collection, but that are available out there and that you can use. So why we created these collections? And the idea was that, for the most part, all the DOE labs that Osni mentioned, all of them had different missions, and they work in different projects. So initially, a group of physicists or computational scientists will have a need, and they will talk to applied mathematicians and develop specific algorithms or techniques, or this will turn into libraries that were used, or programs that were used internally. And, but what we have seen is that in most cases, and what you're going to see here is that the functionality or the application of some of these algorithms can be reused in other contexts. And that's the goal. The goal was to take these tools outside the DOE laboratories. This is money, software that has been spent, well spent, in high-end computing applications, and make it available to a wider group of users. So this is what ACS is about. So ACS stands for Advanced Computational Software Collection. And so, as I mentioned, we don't have all the greatest tools that are out there. So it's a reduced set. Why? Because these are the set of tools that we know that are applicable to today's programs. We have sort of some handle on how these tools are going to evolve and how they are going to be available in future systems. So in order to be able to support the applications that are using, all depend on these tools. So, some of the common things that these have is that, one of the Osni show, a lot of the covers from Science and Nature. And it's amazing because that's something that is very, very recent. 10 years ago, it was very rare to see a computational application on the cover on Nature of Science. So computational science has become a very strong pillar to science today. And what we are looking at this is that, for most cases, we start solving a very small problem. And what we want is to really increase the, either the interaction between the different phenomena and increase the complexity of that problem and increase our modeling capability. So that means that, we are targeting to move or scale our application, the complexity of the problem, and be able to use the computer facilities. That means that as computer power becomes available, we have more processors, more resources allocated to us, we should be able to use the same code and be able to scale without worrying, what is going to happen when I move from 2 processes, to thousands of processes. So those are some of the common issues that all these applications have, and some of the tools to so sort of like the pillar of everything is this sort of what I call the HPC software stack, and several people also have referred different elements of the software stack. But the basic idea is to think that this is an evolving element, and we are sitting on top of this hardware that continues to change. And in the past 30 years, we have seen a lot of funding spent in trying to rewrite the software that suits best this hardware. So right now we are looking at how can we, produce something that is less costly at this level, that we can prototype applications faster and be able to exploit the hardware in a better manner. So that's what this workshop targets. That's sort of like our main goal, and we hope that there is a seat here and there's another one here up front. One here and one here. So, this is an old trend, but just to give you an old chart, which is a couple of years old. But this is the reason why I like to put it is because when we were developing codes, I used to be a postdoc at UCLA, and when we started developing our own atmospheric model, so they had a Fortran 77 code, which I inherited, and one of the charges that we had was to optimize this code and make it work in parallel. Okay, so you take the code, you write your parallel, and we had milestones that we had to commit to, which were performance milestone simulations that we had to, and it was hard. So we had to, really tweak our performance, but we sort of depended on architectures that were, one processor, and I had my MPI. I knew how to split the tasks and just make this parallelism. What this trend suggests is that, we inside a processor now, we have a number of cores, and dealing with another level of concurrency or parallelism is not an easy task anymore. And that's a trend that is going to increase. And a lot of you, as you probably heard about, GPUs or the use of GPUs or combining GPUs and cores. So I'm trying to deal that from the programming environments that we have, the programming models that we have right now is very, very difficult task. So the view of the software stack in reality is like that. And this is how it drives the funding. The funding really now is, you have a tool, it's nice, but we want to see what the tool can do. And there is no better proof that, can you improve any of these applications? Can the tool do better? Do you can just say, oh, I have this code or I have this great idea. You have to link it really with scientific applications. So, sorry. So the idea here of going back to that model where I either inherit a Fortran 77 code that does everything, and then I just have to go and tweak it to make it tunable to a specific machine, is really something that doesn't apply. Because imagine now it's not only the systems that are going to be evolving, but even within a system, the number of cores also change. So depending on what context I use my application, I may need perhaps fewer cores, and then I cannot create like thousands of versions of this code optimized for a particular machine. So I have to do something that is a little bit smarter. So really this, we have to burn and move away from this. And the approach that we're going to promote here is really the use of libraries. Why the use of libraries? Because in many instances, the people that have been developing the libraries and tools that you're going to see in the Axe collection, they have been spending a lot of time doing this or addressing the problem of how can we produce code that is optimized to run on that hardware. What you as a user, what you do is that you sort of call or use functionality that has been expressed there. It's easier because what you do is that you sort of create this level of abstraction. I want to have a linear solver, or I need to invert this matrix. I need to compute a certain number of eigenvalues. You don't have to come down here and speed up your code at this level, but you can sort of remain at a higher level. And there's not only, but there are a lot of references. There's a lot of bibliography. And we, as the tool developers will present today, they may give you some data, on the performance of the tools. And why some of the development choices that were made on that. So, so what it is that with these levels of abstraction, we can think of, imagine you start by discretizing your problem, then you want to solve that problem, and you're going to have something or implement, a number of numerical algorithms and libraries, or you can build, on top of these numerical algorithms, something that fits the kind of problem that you're trying to solve. And you want independence. You really don't want to have to sort of, I want to partition my problem in this way because the complexity of the code that you're working today may increase. So the Axe collection sort of fits in what we call general purpose tools. So they are not targeted for a specific application, but can be used in different contexts. Some common features of the Axe is that, most of them were developed, using a programming model that uses MPI. A lot of the new development is in looking into programming models that will allow them to exploit different levels of concurrency. And if I have time, I sort of show some of the things that we do internally to exploit some different levels of concurrency, using the same tools in the Axe collection. All these tools are downloadable. In most instances, you can go to the websites. If you go to the Axe website, then you can find pointers to the developers, and then the places where you can download the tools. You can install them. In most cases, the only requirement is that some of them are going to ask you, why do you want to use this tool? Or that you sign, so they have a record of who's using the tools. Also, some of them have licenses that if you use this for a commercial, to develop a commercial product, you can do that. But the tools need to be distributed from the developer side. So in most cases, we have very successful development projects that they are commercial products. And all that they do is that, in the scripts, what they have is that they go to the developer site to download the software, and then the code, you use the commercial library. So the functionalities are really in 4 different categories. So Osni and I like to put them in 4 different categories. One is sort of everything that provides some numerical functionality. We have some that sort of extend and help you some level of code development. We have some tools that sort of provide some runtime support and library development. There are a few tools that are also coming from different projects sponsored by the Department of Energy that we hope to integrate. One is the ML library, the Bellows, and Sultan, which we'll have a talk about it in this workshop. ML and Bellows also are going to be referred in trulyknows on Wednesday. And this parallel OSCE, which is a sparse auto-tuning library. OSCE is a sparse auto-tuning library, and POSCE is just an interface for parallel interface to that. So what I'm going to spend time now is looking at different computational problems. And once we take a look at the computational problem, then we're going to see what methodologies are available in the Axe collection. We're going to see what algorithms are available. And so then we narrow sort of the functionality, and we're going to look at what Axe tools provide this functionality. Obviously, this is some of the tools that are going to be presented here. They have been extended in other contexts, so there are other algorithms that are available and that you can also download. So let's take a look at the first computational problem. Let's say that I want to solve a linear system of equations, and I have my system of equations AX equal B, or when I have multiple right-hand side, where I have my multiple vectors x that I need to compute. So the choices are really, first is that I have to see what do I know about the system that I'm about to solve. Do I know anything about the symmetry? First, do I have the metrics computed? Do I have an explicit form of the metrics? Is there a symmetry? Is it non-symmetric? Is it positive, definite, indefinite? The dimension, and the sparsity. Is it a dense problem or is it a sparse problem? And that's sort of what is going to sort of start my choices of, what algorithms should I and methodologies will best apply to the problems that I'm trying to solve. So let's think about the two primary flavors. Will be, a direct method with basically what you're computing is the inverse of the metrics, and you have sort of like an iterative scheme where, at each step you sort of approximate to the solution or compute something that looks like the solution, and you're going to stop until, the distance of what you currently have, the x that you currently have, you are satisfied with that, or, or that's as far as you can converge in that particular problem. So in another alternative is to use a hybrid method. In a hybrid method, you may combine a direct and iterative scheme, and there are several examples. Or, you can have some hybrid methods or preconditioning techniques to accelerate some of these iterative schemes as well. And a lot of that is going to be talked in more detail this week. Also, sort of like the multi-level solvers, algebraic and geometric multigrid, which we'll see some examples here today. If we are trying to solve the problem, it's very interesting because, like maybe 15 years ago, people would say, if you have a very large matrix, don't invert that matrix. So go to an iterative solver. But right now, there are very good codes out there, and you're going to see some examples here. I was just going to talk about SuperLU for the case of sparse, where we are actually solving already very, very large problems with those tools. So, but computationally, we need to be aware of some things. So between the direct and iterative, one of the things with direct is that you can predict exactly the number of floating point operations that would take it to invert that matrix. It's predictable. In the iterative schemes, we don't know because it depends on information that is in your metrics, whether you have it implicit or explicit. Sort of, we don't know how many iterations it's going to take us. In this case, we deal a lot with pivoting. In this one, we may have to use preconditioning, and high likely in many applications people use pivoting. Direct methods have the tendency to be harder to implement. Iteratives are easier to implement, but to scale to large number of codes is kind of tricky, especially all the Krylov based on Krylov subspace method. Direct methods normally involve more communication than what the iteratives do. They require more memory. They require perhaps more complex data structure than your iterative solvers may require. Here, you may have like a graph problem associated with your direct methods, which here is a little bit more simpler scenario for the iterative. So, but the advantage is that once you factorize your metrics, it's easy to solve for multiple right-hand sides, whether in the iterative case, you have to take special care. And that's one of the libraries, or the advantages of libraries like Velos that allows you to do that with iterative kernels. So let's take a look at the first methods. Let's take a look at direct methods. So in X, we have two libraries, Skelepack and SuperLU. So SuperLU is actually for the sparse case. And as Osni is going to mention on Thursday, SuperLU is a library that comes in 3 different flavors. So you have the SuperLU library, which is for sequential codes. And then you have the SuperLU_dist, which is for distributed codes. And then they have one that is for shared memory approach. And Skelepack is actually a parallel version of the LIPACK library, which is the most complete linear algebra package that is out there, the LIPACK. Skelepack has parallelized most of the functionality of LIPACK, except perhaps for 2 other routines that haven't been parallelized. So, there are a number of different algorithms, and really the choice between these algorithms, and Austin is going to spend more time talking about Skelepack, is really, what computational accuracy do you need? Some of these methods obviously are going to be more expensive. Some of these algorithms are more expensive than computational, but give you a more accurate solution. Oops. So in the realm of iterative methods. So we basically have three libraries here. So it's Betsy, as Matt is going to talk about tomorrow in more detail. We have the Aztec OO, which is part of the trulyknows package. And I will give you a flavor of trulyknows. And we are going to have on Thursday also a full tutorial on trulyknows. Then the Hyper library, which is for some preconditioning techniques. And so what I wanted, I just, without stealing the show from Matt tomorrow, what I wanted is just to give you a flavor between the three libraries. So, and remember, right here we are just talking about solving a linear system of equations with an iterative, using an iterative scheme. So one of the nice features of Betsy is the extensibility that you have at different levels. So here we're just looking at sort of what you need for your solving your linear solvers. So Betsy has an interface in C, Fortran, and has some bindings for C++. But you see, the nice feature is these others that are here. So you can add your own solvers. You can use different metrics formats. So if you don't have a metrics, you can use some of these methods with a metrics free. And your operators are sort of your matrices there. In trulyknows, it's another nice framework. They have very nice and robust software as well, but it's for C++, mostly. There is a Fortran interface that more or less works. One of the nice things between the two is that, from Betsy, you can access some of the functionality that is available in trulyknows, and also from trulyknows, you can access some limited functionality that is available in Betsy as well. What that means is that if I start coding my code, and I enter one of, either in the Betsy realm and I start coding my code with that, I don't have to really, write a separate code to use trulyknows. I can access, the functionality from trulyknows from Betsy. And here, the concept is, starting from the basic linear algebra, they have these objects and classes that sort of feed up the line, and you have your linear solvers, eigenvalue solvers, and then you have your nonlinear problems solvers, your ODEs, and and so on. And there's all the different packages, and they have very creative names for all the different packages. So here tomorrow on Thursday, you're going to hear in more detail what each of these packages do. The last one that I mentioned is Hyper, which Hyper also has a very nice interface for Fortran and C. And, and also you can call Hyper from Betsy, and you can access some of the preconditioners that are available in Hyper. One of the things that I like from Hyper is that they sort of have these conceptual interfaces, where tell me what do you know about the problem? What do you have about that problem? And so you not always have to have, your metrics A or, build that metrics A, but you can sort of come from semi-structure, you may have a semi-structure mesh or, structure mesh, and, you can, based on that, they sort of have a selection of solvers that you can use, preconditioners that you can call. One of the things is that what we have noticed is that if you want to solve smaller problems, then this is not the library that you want. This is really for scalable and high performance preconditioners. So if you know that you're going to be solving large problems, then this is a library that you want to invest some time. And one of the nice things, as I mentioned earlier, is that let's say that you start developing your code with Betsy, and you want to try some of the Hyper preconditioners, you can do that. And then you'll have a lot of flexibility, of using Hyper from a framework like Betsy. So one of the things that we had figured out is that, as the users over the years have been developing applications using this codes, something that is common is sort of this your right now is sort of like your MPI, the communication library that is used, and your BLAS, your basic linear algebra, and your LAPACK, that all of these solvers depend. And that's sort of like your first step, that when you sort of want to install the software, you better have either an optimized, and you can get optimized versions of these codes before you start sort of building your either trulyknows, PETC, or Hyper. And also the same goes for SuperLU. So in terms of, there is this family of algorithms, and you have these transparencies in your, so the idea is not that I go through each of them, because we have a lot to cover, but that you look what functionality is available, and you can start asking those questions. And these are the libraries that sort of provide that functionality. So more on iterative solvers, iterative methods. The multi-grid methods, as I mentioned, and something that I should have put was the ML library from trulyknows, which is also one of the multi-grid based preconditioners. So another kind of problems to solve is this linear least squares. And so Skelepack has that functionality, and Osni, I think, is going to talk about both Skelepack and perhaps cover a little bit about the non-parallel version of Skelepack. And when it comes to eigenvalue problems, I'm going to talk on Friday about the slepsee library, which slepsee has been built on top of PETC and therefore inherits a lot of the good features, for scalability. And so you could think that slepsee is going to be sort of the interface to your eigenvalue solvers for sparse eigenvalue solvers. And Skelepack, you will use it for dense kind of cases. So when it comes to nonlinear equations, trulyknows has some functionality. Inside Axe, actually PETC is the only package that we have. And Matt, can we access some of the trulyknows, like the Knox library from PETC? No? Okay. So, but that's what we use. So basically, everything is coming from PETC. Oh, really?
Yeah.
Oh, so, okay, great. So then we have, the nonlinear optimization. So we had one of the packages, which is Tau, which is also built on top of PETC, and that's why tomorrow you will hear PETC first, and then there's a talk on Tau. And it's for, and really, one of the nice things is that, like slepsee, sort of, they define sort of an interface, and they use everything that is in red are things that are coming from the PETC library. So they didn't have to rebuild it. And if you think of that hierarchy, optimizing the code or improving some things, so if this has been done for PETC, then automatically you gain for Tau and you gain for slepsee. And if your application is sitting here, your application benefits from all those layers without having to spend the time developing that. So another family of solvers is this sundials from Lawrence Livermore Laboratory. And this is sort of, we have ODEs solvers. There are nonlinear algebraic equations and differential algebraic equation solvers. And so there are three packages. When you see this S here is the same sort of solver. And interfaces provide also extra routines for sensitivity analysis. And Karen Woodward is going to talk about that tomorrow. So now let's think about, what do I need, to write my parallel programs. So in most of the cases, the three solvers that we talk about, we talk about PETC, Hyper, Skelepack, all of them come with their environment. The idea here is that, you do less of the MPI and you can focus on your actual application for most of them. But let's say that you do need to, there are some things that you may need to implement in parallel, and so, you could think of some of these tools and, so one of the techniques is this shared memory approach where you really don't, even if the machine or the hardware has cores that with memory that is distributed, you could still think that, you want an approach where you don't have to really physically make those divisions in the data. And sort of this is the shared memory and global arrays, which I saw Bruce walking in, Bruce Palmer, who's going to talk about the global arrays library. We have also for complex meshing, generation, and so this is really doing all your discretization, superposing of meshes, and actually calling the solver. And all that is what Overture does. And from Overture, you can even call some of the solvers that are available in PETSI, Hypre. So it's not only, you're not limited only to the Overture provided solver. And this is a very nice package, and we're also going to have a tutorial on Thursday. So handling structured meshes, PETSI has an interface, Hypre also does, and as I mentioned, Overture.
I'm going to do an unstructured example tomorrow.
Oh, excellent. And I think that's what, on Friday, we're going to have a tutorial on Hypre. And they also do sort of a very similar. So you'll see the three different approaches. But the idea here is that you don't have to write your parallel code. So you sort of, you can conceptually think that what you're doing, those operations are being handled in parallel for you. So one important thing is the profiling. And when we think of profiling, in most cases, sometimes we just think, well, how fast can my code go? And here we should think of, algorithmic profiling. If I'm running my code with this, using this algorithm and this solver, is this the best that I can do, or should I try a different, preconditioner, set up preconditioner and solver? That kind of profiling information. And PETSI does a great job about telling you about the memory, the flops, and you can also plot things like the convergence of your solver and get that kind of information. But let's say that I want more general information. PETSI can also tell you about the MPI performance. But if I want to do it in general, I want to do it for any code in any machine, then you have things like what Samir's library, Tau, does. And Tau, what it does is that it's great for working with cores, GPUs, and in a variety of systems. So, for instance, IBM has their own profilers, NVIDIA has their own profilers, Cray has their own profilers, and you can use them. They are quick, and but if you need to move your code to a different platform, then you sort of have to rewrite everything. And Tau sort of is a portable library, so it's supported in all systems, and also access a lot of the hardware information. And Samir can say this with better slides and a great demo. The thing there are two flavors that you can profile your code. Automatic is when you let the library, you just have your code, you don't change a line in your code, and then there are special ways that you either compile your code, or when you execute your code, you ask for a specific information. So the instrumentation of the profile is done in an automatic way for you. Or you can go inside the code and put a specific instructions of what you want to visualize about that. And so, for both PETSI and Tau, that is possible to do that. The last is something that is sort of kind of neat. And and I think it's the trend of a lot of things that we're going to see in the future, is that because there's a lot of dynamic environments, in the machines. I have a processor that may have, over 100 cores, and trying to optimize my code, for 100, or if I use only 64 or 50, is virtually impossible. So one of the nice things is to have these libraries that will take a source code and optimize it, and gives you the object already optimized. And this is better than having just a compile option like -03 or -02. But these guys test a lot of things, and then at the end just said, this is the best configuration for what you have in your hardware. Atlas is one of the early sort of optimizers, and in some of the cases even outperforms some of the vendor-provided libraries. So one of the things that I hope that as people present their talks is to give you the flavor that these tools are also available in many of the vendor-provided scientific libraries. So, and you can access them from interfaces like MATLAB, or in some instances Mathematica. Some of these kernels are even available there. So how do you call these routines? So you're going to be calling them from Fortran, C, or C++ in some instances. So you write your code, and you sort of make a generic code call to the library. What is sort of interesting is this extended functionality that you can do at at runtime. So in tools like Petsy, and because of Petsy, slepsee, and Tau had that functionality, is where you don't have to really make certain choices inside your code. But let's say that you can try runs where you change the solvers or you change some parameters that you pass to that solver, and you do it at runtime. So you don't have to go inside your code and modify the code, compile it, and then run it. But you can imagine that you can put it in a loop where you can try different a set of solvers. And also, when you are profiling with Tau, you can pass certain parameters at runtime similarly. So this is a feature. And we are looking, so our way to extend some of the functionality or optimize it in machines like also mentioned, like in Hopper, the Hopper has 24 cores. What we do is that we added some extra keywords that go or use specifically for deciding, which tune library to use. And they are plugged, in all the interfaces of all the libraries. And then, so as I mentioned, the idea is to really that you focus on the science. And, when we were reviewing the applications, we tried to see, who could benefit from this. So this is, don't write the code yourself. Don't write a monolithic code, but write something that you think that is going to be useful. And that once you finish your application code, there are people that will not know how you develop that, but they want to use it to solve a variety of problems. So tool interoperability, I sort of mentioned, this is sort of kind of tool. If I'm working already in Petsy, do I really have to know SuperLU or try SuperLU? So there's this interoperability, which allows you from Petsy, you can call SuperLU, you can call trulyknows, so you don't have to write that code yourself in both libraries. And trulyknows likewise has some level of interoperability. I'm going to skip this in interest of time, and also because Matt and the trulyknows people are going to talk a little bit about this. So just in general, I'm going to take a Skelepack, but it's very similar. So as I mentioned, go to the websites. You download the tools, and one of the things that you want to do is you need to have your communication library, MPI in most cases, because all of the tools that we're going to be looking in the X collection, all of them are parallel tools. And then you have to have a very good versions perhaps of LAPACK and BLAST for most of the tools. Okay, so this is just some of the things that we are doing here is that we are looking at kernels that sort of are used inside many of these routines. And the idea here is, to do that level of auto-tuning and drive the auto-tunings that later the libraries in the Axe collection, and you may wonder, why are you doing this? And the reason is that we want the codes to always be able to scale. We want to always be able to get the maximum performance in the system without really having to change the interfaces. And you as a user, you don't want to be bugged with details on the interfaces and how the implementations work. So in order to do that, we have to do it automatically. We cannot do it, put it in the interface. So the idea here is that we start with a prototype. I know that Matt doesn't like the idea of starting with a prototype. For me, with a prototype, it's a good, you have a simple code. You're going to see tons of examples in C, Fortran, and different flavors. You take one of those, you look at it. Once you understand it, you can sort of, build hopefully minimize the time to solution for you to have a code that you can call, this is my production code. Once you have this, obviously we have to leave, where the complexity. This little model that I wrote, when I start adding more phenomena or I increase the resolution of the model, what things are going to change and what things are going to remain. So you have to sort of think about that, the software evolution. Sustained performance is important because, we don't want to repeat the errors that we did. People would put a graduate student or a postdoc, and we spend a lot of time optimizing a code that 2 years down the road was useless because the system changed completely. So the idea is to write something that is very, very flexible. And we think that with the approach of having the libraries, that's what we are sort of achieving, maximizing the life of the software that we produce and the resource utilization in the system. So with that, it's just so if you look at the agenda, so we are going to sort of spend equal time talking about these large projects, Betsy and Trulyknows, tomorrow and on Thursday. And just for schedule, normally I put slepsee also on the same day that we had Betsy, just for continuity, but we had a schedule conflict and we had to move slepsee for Friday. Today also is going to be talking about Skelepack. And the breaks are long enough, so we do want to encourage discussions. Please ask us questions. I mean, we have 4 days. I know that it's towards the end. We're going to be all very tired, but in our experience is that we have seen the progress that people have made, after the workshop, and also it's a good place for networking. If you're looking for a postdoc, you're about to graduate, and you see something that somebody talks about an application, this is the time that you should talk to them. If you're a postdoc and looking for a permanent position at one of the labs, which of course I have nothing but encourage that, talk to us about it. And then we have the other tools in the afternoon. The only time that changes is Friday, where we will break a little bit, half an hour later. We have an invited talk, and normally we do the invited talk either on an application or on more on general high performance issues of computational science. But this year we decided that we wanted an invited talk that talks about something that is hot topic, and is the programming environments. So this is going to be a programming, because why? Because a lot of people are thinking now, oh, should I rewrite my code in CUDA? What should I do? CUDA MPI and all this. So Kathy is going to give you a very good introduction to all that tomorrow. And lastly, as you know, all of you are invited to our dinner tonight, and is sort of in a place that is on campus. When you see that big tower, it's very close where the clock tower is, the Campanile. And I want to thank Paratools, who is the provider of, because we cannot buy any alcohol, and they are going to provide wine tonight. So thank you. Okay, so now I just want to talk about the logistics. So all of you that returned your signed your user policy, you got an account. And your account should have sort of like a number, train something. And that train something is your computer, your login. So you type, train 1 to train 50, so one of those numbers. So something that is important is that, these resources are being heavily used in production time. So, but for the AXE workshop, we have an allocation. But the allocation of certain nodes only work with the train accounts. So if you already have an account with NERSC, you use this train if you want to do some of the practices, because you can do that interactively. Your account may not allow you to get some of those resources. Under your training account, you also have, that's the password, that starts with a C1 something. So that's the password that you need to type for. And the machine that we're going to be using is Carver at nersc.gov, and Harvey is going to give a little tutorial later today on introducing you on some important issues about Harvard. So if you order special meals, instead of Ying, you have to see Kathy, who is outside. And also, they can tell you about a list of restaurants for the evenings. Afterwards, there are plenty in Berkeley. And we just want to thank, the Department of Energy for sponsoring this activity. Also, Harvey from NERSC that came and is going to help us, and Catherine Day, who is outside and has been working in the logistics of this. And I forgot, and Rachel Lance, who's been working with some of you with the travel, and the University of Oregon, and Paratool. Actually, Samir has been, over the years, it has been supporting a lot of our activities that we have, and we have this, live DVDs and bootable images that you can download, and if we had talked or communicated, we could have printed that in a DVD. But the good news is that you can go to the website, and it had pre-installed versions of the tools. And so in this case, you don't have to install the tools. You just you are in a virtual environment that contains all the tools, all the examples, and some of the exercises that are going to be seen here. Okay, so are there any questions? No? Or anything that you would like to, yes? No? So, Samir?
I have some USB sticks if someone wants to install the live DVD.
Right. Okay. So yes, so somebody needs to do that, and this work for any system, whether you have a Mac or a PC, you can boot it in. Hopefully, it will work. Okay, and so I think we're going to take a break. But before we take a break, we're going to go around the room, yes. And if we can just here, introduce yourself and say what you work on. And so we'll start with you. Oh, okay, sorry. Yes.
All right. I'm Chris Garrett.
You want to plug in here?
I don't know if I care. I'm Chris Garrett. I
Okay.
talk to lots of people.
Can you
in
use the mic?
So I don't really care.
Is it?
Hello? Is it on?
It's on, I think. That's it. Well, the only reason is because.
Hear me.
Let's see. Huh. Yeah, no, it is.
All right. They tell me it's on. All right. I'm Chris Garrett. I go to the University of Texas at Arlington. I'm a PhD student there, and I have also worked at Oak Ridge National Lab, where I've worked with like neutron physics codes. So I guess that's it.
Hi, I'm Xiangdong Liang. I'm a graduate student in MIT Applied Math. So I'm working on the physical mathematical modeling and the computation. Right now I'm working on computational electromagnetism, basically designing a microcavity stuff.
Hi, I'm Omid. I go to Florida State University. I work on inverse problems with spectral methods.
Hi, I'm Lindsay Erickson. I'm at Sandia National Labs. I work on interface methods and electrohydrodynamics. And we have 2 open staff positions. So talk to me about that if you're looking for a position.
Hi, my name is Yuri Feldman. I'm from Caltech. I'm working on computational fluid dynamics, heat transfer problems, and we have a specific project that I'm working on is a project with JPL. We are working on a Titan Montgolfier, which is a hot balloon.
Hi, my name is Scott Small. I'm a postdoc with the Iowa Flood Center, which is part of the University of Iowa. I am working on computational methods for a real-time flood forecasting system.
My name is Hyunjin Kim. I work at a startup company called HeartFlow. I develop computational methods for biofluid applications, and I've been a user of trulyknows and slepsee, so it's a good opportunity to participate.
Hi, I'm Valentin Senecolt. I'm doing an internship at LBNL, and I'm working on communication with algorithms and GPU clusters.
Hi, I'm Cristianto. Call me Chris. I'm a postdoc at Minnesota, and I'm doing CFD pretty much with a lot of system application. Right now I'm doing it more in the modeling the crystal code from the mail.
Hi, I'm Nathan Gibson. I'm an assistant professor in mathematics at Oregon State University. Some of my projects are on computational electromagnetics, advection diffusion problems, and uncertainty quantification in reservoir network modeling.
Hi, I'm Saurabh Ugerkar. I'm a PhD student at the University of Southern California. And I work on system software and architectures for high-performance computing. And I specifically look at the problem of fault tolerance. Yeah.
My name is Sherwood Richards, and I'm a graduate student at Caltech doing simulations of core collapse supernova explosions.
Hi, my name is Ross Ingram. I'm a mathematician at the Bettis Atomic Power Laboratory.
Hi, my name is Tipalakriti again. I'm from Cornell University in applied math. I developed algorithm for expensive function, like using circuit optimization.
Hi, my name is Patrick Farrell. I'm a postdoc at Imperial College London, and I work on adjoint PDE constraint optimization and stability analyses.
Hi, my name is Garnet Vaz. I'm doing my PhD at University of California, Merced, and I study topology changes in networks.
Hi, my name is Diego Glendo. I'm a postdoc at Oak Ridge National Lab, and I've done algorithm development for the Madness and Indigo software packages.
Hello, my name is Manuel Rodriguez. I'm working as a postmaster at Oak Ridge National Lab, and I'm working on adaptive mesh-refined libraries.
I'm Curtis Lee. I'm a grad student at Duke University, and I'm doing ocean wave simulation for energy capturing applications.
I'm Sam Skillman. I'm at the University of Colorado as a PhD student in astrophysics, and I do cosmological simulations using an adaptive mesh refinement code.
Hi, my name is Eva Sunny, and I'm a PhD student at the University of Michigan in Ann Arbor. My specialization is in fission and radiation transport theory, and I'm working on computational methods for reactor analysis.
Hi, my name is Lucy Dai. I'm from the University of Kentucky, and I'm a PhD student. I'm working on the multigrid methods for solving PDEs.
Hi, my name is Xiaojue Gong. I came from Stony Brook University, and my research is on computational fluid dynamics.
Hi, my name is Paxing Lee. I work here in the astronomy department, and I'm working on star formation simulations.
I'm Dina Hanoun. I'm a graduate student at North Carolina State University, and I'm working on CFD simulations.
Hi, I'm Samir Shendev. I'm from the University of Oregon and Paratools Inc. I work on the Tau performance system as well as the HPC Linux live DVD project. Thank you.
Hi, I'm Huipeng Rui. I'm the graduate student in Dallas State University. I'm working on the simulation of laser and plasma by solving the Maxwell equations by FDTD method.
Hi, my name is Yuhe Wang. I'm a PhD student in petroleum engineering at Texas A&M. I'm working on high-performance computing for reservoir simulation.
Hi, my name is Yuan Zhexi. I'm from the Math Department of Purdue University. I'm working on the fast algorithms for the structure and the sparse matrix.
Hi, my name is Yan Li. I'm from Stony Brook University, and I'm working on a simulation on parachute.
My name is Jennifer Frederick. I'm a grad student here at Berkeley. My research is in CFD relating to methane hydrates and two-phase flow.
I'm Brian Brennan. I'm currently a PhD student at Baylor in the mathematics program, working on code generation for various finite element methods.
Hi, I'm Matt Nepley. I work on PETSI. I have for more than a decade.